So let's extend our model from the least squares fit of a sinusoid to the following. So we could say that f of t is equal to a naught plus a1 cos omega naught t plus b1 sine omega naught t plus a2 cos of 2 times omega naught t plus b2 sine 2 times omega naught t plus all the way to am cos of m multiplied by omega naught t plus b of m sine of m omega naught t. That is for the case where they're equally spaced. And we know that, okay, so from this we can deduce that a naught is the sum of y divided by n, where n is our number of data points, and a of L is equal to 2 over n, sum of y cos of L multiplied by omega naught t, b of L is equal to 2 over n multiplied by y sine L omega naught t, everywhere for L equal to 1, 2, all the way to m. So we can use this to fit data in the usual regression sense, where we have the number of data points greater than the condition in 2m plus 1. And but an alternative way is to say that, well, if we have n equal to 2m plus 1, so the number of data points equals the number of conditions that we need to meet, then this approach is what is used in the Fourier series. Okay, so the Fourier series arose from the mathematician Fourier, who was studying heat flow problems. And what he showed is that any arbitrary periodic function can be represented by an infinite series of sinusoids of harmonically related frequencies. So that is f of t is equal to a naught plus the sum from k equals 1 to infinity of ak cos k omega naught t plus bk sine k omega naught t, where omega naught is the fundamental frequency, 2 pi over t, and k multiplied by omega naught is all the harmonics of that fundamental frequency. Now, the coefficients, we're not going to go through the proof, but the proof is very similar to our least squared regression argument. The coefficients can be found as follows. So a naught is equal to 1 over t multiplied by the integral from 0 to t f of t dt. ak is equal to 2 over t multiplied by the integral from 0 to t of f of t cos k omega naught t dt, and b of k is equal to 2 over t times integral from 0 to t of f of t multiplied by cos of, sorry, it's not cos, sine of k omega naught t dt, for k being 1 to infinity. Okay, so what the Fourier analysis then says is that we can, if we sum these sinusoids, we'll be able to interpret a function in terms of these sinusoid, and the harmonics of the fundamental frequency. Now this is really important because the flip side of this is that if we have a set of data points, let's say n data points, we could use this to fit or to find all the sinusoids that would fit that data set. And if we can find those data points, we can then look at fundamental frequencies or harmonics in our system that perhaps describe certain physical properties. We're not going to go into that because it's out of the scope of our coursework, but it's an interesting thing to think about. So those vibrations that you feel on that bridge, if you had a little logger log in all of that information using the concept of the Fourier series, you could find the fundamental modes or frequencies of those vibrations, which will tell you the resilience of your structure, because you'll be able to design it for those different modes or frequencies. So let's do a quick example on the Fourier transform. Sorry, Fourier series.